John, can you give me a heads up if you can hear me?
Yes, I can hear you.
Awesome. Alrighty. Okay, so today we're going to be talking about convexity. And let me hide this. Alrighty, so when we think about convexity, what we're talking about is in the whole world of optimization, right? There's a subpart of it, of all the types of optimization problems that are called convex optimization problems. Right? And even within that small set, there's another little one right here called linear programming. Right? So what we've been studying is this little red set for a bit. But the broader set that it's contained in is convex optimization. And then, of course, more globally, we have just optimization in general. All right. So what we're going to talk about today is what exactly convex optimization problem is and why is it special. So broadly, when we think about optimization, so any sort of optimization problem, we're talking about a maximization or minimization of some function over X, and we're going to minimize or maximize over those variables, subject to some constraints where X has to be an element of some set. Now, typically, the set that we worked with in linear programs, the set of X was given by all X that satisfied AX is less than or equal to B. Right? So usually we would just write this equation. Now, all I'm saying is we're going to generalize this a bit more to constraints that aren't necessarily linear equations. Now, broadly, what happens when we're doing applied optimization is that computers will be asked to search for the optimal value. So they're trying to find this X star. And as a result of that, they can tell us also what the objective function is. Now, the thing about convex optimization problems is that they're actually easier for computers to solve. Right. So what I want to do is give you a brief understanding of why that's the case. And we're going to just sort of use toy examples that kind of explain what's going on. Let's say we had a very simple sort of toy problem where we had somebody in a room and they're blindfolded. Okay, so here goes our person and they have a blindfold on. And somewhere in that room, there's a fire pit, all right? Now this person is a little bit cold, and so their goal is to find the fire pit with their eyes closed or blindfolded. Now it ends up, this is almost exactly the same idea of what a computer is doing, right? And we'll sort of see why. If we think about this fire, it's going to be giving off heat that the further away you are from it, the less you feel it, right? But you can certainly feel the heat given off by the fire, and you might be able to sort of figure out what direction it's going in, right? And so ultimately, this person who's blindfolded, they're going to sort of meander towards the fire, right? And each step, they're going to get closer and closer. They're going to feel it warmer and warmer. So along that path, right? Or let's say we are to draw a line from here to here, right? That passes through the fire. And if we were to draw a graph of the temperature, right? You might see something like that, right? And so what's going to happen is this person, as they walk towards the fire, right, they're going to feel it get warmer and warmer and warmer. At which point, it's going to be the hottest right where the fire is, right? And they're going to sense, well, maybe, at least a computer would sense, maybe not a human, that the derivative right here is 0. And at that point, we're going to know, or the computer is going to know, to stop. Now, this problem is relatively easy for a variety of reasons. One is there's only one fire in that room, and the other is there's no blockages. And so if our goal is to find the hottest place, it's pretty easy. So let me sort of draw these two counter examples, and it will give you some indication of how problems get harder for computers to solve. So let's say we had the same problem where our goal was to find the hottest spot in the room. And again, we had a fire over here, and let's pretend this is a really big fire. Okay. And on the other end of the room, we had a small little fire, maybe even just a candle, right? Now, each one of these is going to give off heat, right? And I'll draw them in different colors. And of course, the small fire is going to give off a lot less heat, but nonetheless, it will give off heat. And so if we have this person in the room blindfolded, and again, we draw this line. We're going to draw it across the room, and we'll draw it so it connects through the two fires, right? If I were to draw what the temperature is along that line, we might see something like this, right? So a little fire right there, and then a big fire on the other end of the room. Now, if our person is standing closer to the little fire, they might think that the hottest part of the room is actually in the direction of the little fire, right? When really, the hottest part of the room is in the other direction, right? And the problem is where they're standing. So if they're standing at some point right over here, they're going to feel that little fire more. Right? So they're going to go, oh, well, the bigger fire must be, you know, well, I guess depending on the person, to the right of me, right? Or to the left, however you want, you know, in this direction. And so they're going to walk in that direction because they feel it warmer going in that way. Now, if they happened, let's say, you know, somebody else was in this situation and they were standing over here, in that case, they would feel the bigger fire, right? So that would be the equivalent of, you know, somebody standing over here. So they would feel the bigger fire moving in that direction. So they would move to the right of the screen. Okay. And so this is a big problem in optimization when we have multiple local optimums. Okay. So this is bad. If we have multiple local optimums, it's hard to figure out where the global optimum is. Sometimes, depending on where we start, we might think one optimum that we find is actually the global one when it in fact is not. Okay, so that's sort of a fundamental issues that we have in optimization that a computer is going to go through. Now, whenever you see problems like this, and we'll go into this a little bit more, where you have multiple optimums, this is not a convex problem. We'll go into some of the mathematical definitions of what convexity is when it comes to the cost function. So here, what I'm plotting here, again, is like the cost function. So here is the cost function. Okay. Now, there's one other issue that also presents an difficulty for optimization algorithms, in particular computers, to solve optimization programs that have to deal with convexity. And this convexity issue has to do with the constraint space. So again, we're gonna draw our room. We're gonna pretend we have a little fire right there. And we have our person who's blindfolded, right? And normally they would just walk, directly towards the fire. But let's say we put a wall right here. Okay. That's blocking them. They're still going to feel some radiated heat, right? But it's going to sort of distort the field, okay? Not only that, as they walk, let's say they walk towards the heat, and maybe they walk this way, they might end up getting stuck on the wall and trapped on the wall, right? And they're going to go, oh, I can't go any further to the right. So where I am against this wall is the optimal solution. Now, clearly that's not right, because the person might have just been able to, if they had known a little bit more, they could have walked around the wall. Right? And so this is a non-convex problem. And it's non-convex because of the feasible space. Or we could say non-convex because of the constraint equations. And so the reality is most computer algorithms aren't particularly smart, right? They don't, okay, yeah, if we look at a room, we can sort of figure it out. But when we're dealing with hundreds, thousands, or hundreds of thousands of dimensions, what does it mean to go around the wall, right? Or what does a wall even mean? And this is really hard for a computer to address, right? So non-convex problems can be introduced either through the cost function or the constraints. Now, the easy problems, as I said, these convex problems, convex optimization problems, they're convex in the objective function. And they're also convex in the constraint equations. So in order to be a convex optimization problems, both these things need to be true. If one of them isn't true, then you have a non-convex problem. Again, it's going to make your problem typically a little bit harder to solve. All right. So the sort of follow-up is, what the heck is convexity? And you guys actually probably learned about convexity at one point. So in calculus, you had some functions and you said, oh, let's take the double derivative of my function. And that would tell us, in this case, we have concave down, right? And then sometimes you learned about concave up functions. All right, so that's all we're talking about. So it's the same idea, right, that you might have learned in calculus, or at least a related idea. All right. So in order to have a mathematical definition of what convexity is for functions and sets, we need to introduce a mathematical tool first. So what I'm going to do is I'm going to say, let's pretend we have 2 points. So there's going to be x1 and there's going to be x2. And this can be in one-dimensional space, two-dimensional space, or it can be in hyper-dimensional space. Doesn't really matter. And we're going to have a line segment between these 2 points. So here I'm drawing it as 2D, but again, it can be, it could be in 3D space like that. That would be fine, right? Or 4D or 5D or 6D, whatever. All right. Now, the neat part is any point, so I'll call this, I don't know, we'll call it x prime. Any point x prime can be represented as a weighted average between x1 and x2. And typically we write that weighted average as follows. So we're going to say theta times x1 plus 1 minus theta times x2, where theta is between 0 and 1. So that should be 0. How do we think about this? Well, when theta, write it over here because it's not. When theta is equal to 0, then x prime is equal to x2. When theta is equal to 1, if you work out these equations, right, then this quantity 1 minus 1 will be 0. So you're going to have none of x2, but you'll get 1 times x1. So in this case, then x prime is equal to x1. And so if we want to relate that on our graph, theta equals 0 is this point. And theta equals 1 is equal to x1. And if I wanted to generate any other point, so let's say I wanted to do this one, which was 1/3 of the way, then I would select theta is equal to 2/3. Right? Or if I wanted to go, let's say this 40% of the way, or whatever, it's a 60-40 split, then here that would correspond to theta equals 0.4. Right? And so what happens is, no matter what theta we pick, we can generate a point along this line here between x1 and x2. So in some ways, we can think of this convex combination well, this is just sort of like a weighted average of 2 points. All right, so we have this idea of a convex combination between 2 points. And we're going to use this convex combination in order to identify what is a convex set and what is a convex function. First, let's talk about convex sets. All right. So a convex set, let's write this. So I'm going to give a definition here. A set is convex if for any 2 points so set S is convex if any 2 points in S if for any 2 points in S, the line connecting them is also in S. I should say fully contained in S. Now, mathematically, we would write that as saying S is convex if and only if for x1, x2. Actually, I would say for all x1 and x2 in the set and for any theta between 0 and 1 that theta x1 plus 1 minus theta x2 is also in the set. Now, I think the easiest way to sort of understand this is to visualize it. So I'm going to draw a convex set, and then I'll sort of draw out what I mean. So let's say we had constraints that made the feasible set this box right here. So it's everything inside of here. Okay. I could pick any 2 points arbitrarily and draw a line connecting them, and that line stays within the feasible set. And it doesn't matter where I pick my points within the set, it's always going to stay inside. So that's sort of our test to figure out if something is convex. Now, a convex set doesn't have to be a pretty box, right? It can be any sort of shape. Let's say I had a constraint that said you have to be less than some line or greater than some line, but less than a parabola. So it'd be this area right here, shaded in. This is also a convex set. Right? So I could pick any 2 points, no matter where they are. If I draw the line connecting them, that line is still within the set. This even works for infinite sets. So let's say I had a pi slice here that went off to infinity. Okay. This is also a convex set. Oop, oop, oop. I'll do a few more because these I think are always good examples. let's say we have a line. So here goes the XY axis. We have a line, and we say all points have to be on that line. Well, that's also a convex set, right? So if I pick any 2 points on that line and then I draw a line connecting them, that line is still on the line. So a line, right, is also a convex set. That's kind of cool. And for the last example, let's start with a circle. So a circle is a convex set. Now let's say I intersected that circle with 2 other circles. So now we have this space right here. So that's the common intersection between all 3 sets. This is also a convex set, right? So no matter where I draw these points and lines, it's still going to remain within the set. Now with that, maybe we can give a few examples of some non-convex sets, and hopefully that will, provide some insight. All right. Let's say we had something like a kidney bean shape. All right, it's not convex because I can pick 2 points right here, and if I try to draw a line connecting them, then part of that line is outside of the set. So this is a good example of that. So usually this line test is pretty indicative of whether you're convex or not. Let's say my convex set was the union of a bunch of different circles. So I said you could be inside of this circle or that circle. Well, this is non-convex. And again, because if I pick a point here and a point here, and I try to connect them, then part of that connecting line is outside of the feasible set. So if you have a disjoint set, well, I don't want to say disjoint because technically disjoint could be like right next to each other. But if you have a set where each of your feasible spaces are separated, then that as well is infeasible. Okay. Or not infeasible, and non-convex, sorry. Another example is, let's say we had the following. Okay. So this whole area, we could write it as, we could write it as a set of linear equations. Let's pretend. So it might look something, I'm going to do my best to replicate what I have in the notes. That. All right, so let's say I had a problem, maybe I was saying minimize 5x1 plus 10x2, subject to constraints that correspond to the lines. So we might have 3x1 plus 5x2 is less than or equal to 15. x1 minus x2 is less than or equal to 3. And finally, x1 minus x2 is less than or equal to 0, where, but we're going to add one more constraint where x1 and x2, instead of being real numbers, right, they have to be integers. Okay, so that means our only feasible points are those that are integer values. Okay, so maybe. So only these yellow points can actually be used as part of the solution. Now, if you think about it that way, then this is absolutely not a convex set, right? So I could pick 2 points that are part of that set, but if I try to connect them, right, they're not part of that feasible set because instead of being integers, let's say this point right here, that's like a fractional value, right? So it's not an integer. It's not part of that feasible set that we required. Now, another little example that sort of trips people up sometimes has to do with circles. So everybody thinks, oh, a circle is convex, right? So maybe I have a circle like this, right? And I have some optimization problem where I say minimize, again, doesn't really matter, 5x1 plus 10x2, subject to the constraint that x1 squared plus x2 squared is greater than or equal to 4. Okay. So in this case, we're not talking about stuff that's inside the circle. We're talking about everything that's outside of the circle. Okay. So we're looking at all points that have a radius of greater than 4. Okay. So again, if we were to pick 2 points, so the green points are definitely inside of the feasible set. But if we try to connect them, they pass through this infeasible part. So it's like this donut hole. Right? So these are all, examples that you might encounter with convex and non-convex sets. All right. Okay. So the first thing that we want to go back and sort of relate this to what we've done before is we can talk about, well, what about linear equations? Are those convex? Well, it ends up that they are. So, so let's say, we can have our standard minimization problem. It's going to be subject to the following constraints. All right. So these are all linear equations. All right. And again, we could always write this in some sort of matrix form. So we might have minimized C transpose X such that, AX is equal to B. All right. As a general rule, this is always going to be convex. And it doesn't matter if we're talking about having our constraint equation be an equality or inequality. So AX is less than or equal to B is also a convex set. All right, so if we can write our constraint equations in either one of these forms, then it's convex. See if I can prove that really quickly. So let's say we had an x1. So suppose we have an x1 that is equal to ax, well, a times x1 is equal to b. And there exists an S2 where AX2 is equal to B. Right? So the question becomes, if we try some third point given by the weighted average of x1 and x2, will that also satisfy the linear equation a times x prime is equal to b? So we can sort of check that really quickly, right? So let's go ahead and start plugging stuff in. So for x prime, we're just going to have theta x1 plus 1 minus theta x2. And again, the question is that equal to b? So if we start multiplying stuff out, I'm gonna pull out this theta, but we end up with a times x1 times theta. And we get 1 minus theta times a times x2. Now we already know that a times x1, well, that's just equal to b, right? And theta is just theta. So we have that quantity on the left-hand side is equal to theta times b. And on the right-hand side, we know a times x2 is also equal to b. So we're left with 1 minus theta times b. From there, we can multiply this out if we want. So we get theta times b plus b minus theta b. And of course, we get this cancellation right there. And it ends up that we're left with just b. Right? So in fact, b is equal to b. Right? So that tells us that any x prime will satisfy the constraint ax prime is equal to b. Right? So this tells us that the constraint ax is equal to b is convex. And this is always true. It doesn't matter what your a and b is. It will always be convex. So that's pretty cool. All right. So linear equations are convex. The next set that is of particular interest are called Euclidean balls and ellipsoids. And these are basically just circles, right? But in hyperdimensional space. So previously we had seen that a ball in 2D space again, this is sort of a circle, okay, is convex. Okay. So again, here goes my circle. My feasible space is everything that's inside of it. If I pick any 2 points and try to connect it, it will stay within that circle. So we know this ball, this Euclidean, our 2D circle, right, is convex. Now, this holds broadly true, regardless of whether we're working in 1 dimension or 2 dimensions or 3 dimensions. If we have any sort of ball that we can define by a center point and a radius, so here I'm going to say the ball centered at xc with radius r, well, maybe that's just given by the set of all x such that xc1 minus x1 squared plus xc2 minus x2 squared is less than or equal to r squared. And so all that we're doing with this equation is we're saying, all right, well, right here will be xc1, and this is xc2. And anything center in the circle, right? So here goes our circle with radius r. Well, that's convex, okay? And I can move that circle around anywhere in this Cartesian plane, or I can make the circle bigger or smaller. It's still convex. So a lot of times, you might see this constraint written up in an optimization. So you might see minimize f of x subject to, we can sort of take this guy. We can write it into our constraint equation. And there we go, right? So we no longer have a linear problem we have a nonlinear problem, but at least it's convex. Okay. Now, people don't really like writing things this way, writing out the quadratic equation for a circle. So a lot of times we use norms. So the equivalent way of writing this is we can write this as minimize f of x such that the norm, and here we're talking about the 2 norm, is less than r. Right? So, and xc is just corresponding to the coefficients here. So it's going to be a vector equation. So normally people like writing it like I've just written. Now, what is the norm? Well, I think we learned this in our first lecture. So you might recall that the norm of a vector is just equal, if we're talking about the 2 norm, that's equal to the square root of the square of all its components. So it's going to be y1 squared plus y2 squared. Now, normally this is for 2D, but if you have 3D, then you add the third component and square it. And well, you could do this for however many components you have. So if you have an n-dimensional vector, then you're going to square each component in that vector and take the square root of it. Now, the shift with xc, right? So the centering, oops, and sorry, it should be you there. We can certainly do shifting as well. That's not a problem. So we could say, well, what if we wanted our circle centered somewhere else, right? So in this case, we would say, well, what if we want it centered at xc minus x, right? So instead of u, we're going to have xc minus x. Right? So if we're talking about that ball, right? So that's how I wrote it up here. That's just equal to xc1 minus x1 squared plus xc2 minus x2 squared plus xc3 minus x3 squared, and so on, right? All the way up to however many dimensions it is. So we'll say x to the n squared. And so this is the same idea, right? So we don't just have to restrict ourselves to 1, 2, or 3 dimensions. We go to 100 dimensions if we wanted. Now, there's other ways of representing this. So we could absolutely, if we take this constraint, we could expand it out. So we started off with, we have a such that xc minus x, taking the L2 norm, is less than or equal to r. If we substitute in that square root, that's certainly fine. It just makes things a little bit uglier. So I'm going to sort of shorten the notation. I'm not going to write out all the x's. So we could write that. Now, to make life a little bit easier, we could just square both sides. So we end up with the following. Okay. And this actually makes life a lot easier for us. So a lot of times, And we'll see why in Cplex. The way you write it here is actually how Cplex would take it. Right. This is called a quadratic equation, or a quadratic constraint, sorry. And it ends up that this is something that we can write in Cplex fairly easily. You might need to expand it out, but you could at least write it. Okay. Cplex can't handle square roots, so it's not really designed to handle square roots, but it can handle squared quantities. Okay. Now, one thing that is pretty useful is a lot of times you'll see people write these quadratic constraint equations in different ways. You know, because these are norms, and these norms are essentially inner products as well, right? So another way that we could write this, so if we think about what's going on here, this is the same thing as, like this whole thing is sort of the same as saying, if we're working with vectors, x minus xc transpose times x minus xc is less than or equal to r squared. So it is the same idea. Now, if we were to do this in 2 dimensions, just as an example, right? So using the same values, then we could certainly go ahead and start substituting stuff in. So we'd get x1 and x2. And we'd get xc1 and xc2. Right? And we're going to take the transpose of that and multiply it by itself. So this allows us to, we can certainly simplify this. Or not simplify it, sort of put it all together. So in the top part of the vector, we'd have x1 minus xc1, and on the bottom, we'd have x2 minus xc2. We're going to take the transpose of that and multiply it times x1 minus xc1 and x2 minus xc2. All right. If we go through that multiplication, again, so this is sort of gets turned sideways. So it's going to look like that. Right? So you're going to have one value and another, and then we're going to multiply it times a column vector. And so the output of this whole thing is equal to x1 minus xc1 times x1 minus xc1 plus x2 minus xc2 times x2 minus xc2, and that's all less than or equal to r squared. Again, this is exactly what we've written up here, you'll notice, okay? So if we multiply this out, right, or not multiply it, but sort of group it a little bit better, we have x1 minus xc1 squared plus x2 minus xc2 squared is less than or equal to r squared. And again, this is what I told you Cplex can handle quite well, right? So this is the same thing as our original circle equation. So what we can see is we have a bunch of different ways to write the constraint equation to represent a circle. So here goes one way to represent a 2D circle. But again, you can also represent a 2D circle using this norm equation up here. Okay. Or in fact, again, sometimes people make it a little bit easier and they say, well, let's just square it because we're gonna, we need to square it anyways. So usually folks write it like the following. Okay, so these are two equivalent representations. All right, so just one of them is in vector form and the other is sort of written out algebraically. But they represent the same idea. All right, so we know how to draw circles. That's great. If we want a more complicated shape, for example, an ellipsoid, that's actually certainly doable. All right, so an ellipsoid is certainly a convex shape. Again, we can pick any 2 points in there. So here goes my set that I'm trying to represent, and it's written, can be written by an ellipsoid. This function is also convex. There is a useful way of representing ellipsoids. Right? So let's just say we had some minimization and we have some function f of x. The way that we often write an ellipsoid out is similar to a quadratic. But in between the two x minus xc terms, oftentimes you'll see this P inverse, okay? Now, if P inverse is equal to the identity matrix, then the feasible set is a ball. Or it's a circle, right, of unit 1. Alternatively, if P inverse sort of has this diagonal structure where we have values along the diagonal. So here I'm going to write it as 1 over lambda n squared, and then zeros everywhere else. Well, that corresponds to an ellipse where the lambda 1, 2, and 3, 4, 5 all the way to n. Well, these correspond to the major and minor axes of the ellipse. Okay, so let's do a little example of what that might look like, just to give you some indication. And in fact, I'll sort of work it out, and maybe you'll sort of understand what's going on. So let's say we had the following example where we had x minus xc. And I'm going to do 1/4, 0, 0, 1/16. So this is the same thing as my P inverse. So we're going to assume that's P inverse. And we're going to have x minus xc is less than or equal to 1. Okay. All right. So if we went through and started doing this multiplication, and I'm going to do it in 2D, right? So this quantity here is just a vector, and that needs a transpose. So it's going to be a vector that looks like x1 minus xc1, and then x2 minus xc2. And likewise, this guy's right here is going to be a column vector where we have x1 minus xc1 and x2 minus xc2. So let's go ahead and do this multiplication really quickly. So if we multiply the vector times the matrix, so we're going to do, row times column, right? We end up with a row vector. So this multiplication, if we work it out, it's equal to 1/4 x1 minus xc1 plus 1/16 of x2 minus xc2. So that's just the multiplication between the row vector on the left with the matrix, and then we're going to multiply it times the vector on the right, which again is x1 minus xc1 and x2 minus xc2. Oh, and this is not a plus, that should be a comma. So now we can multiply this row vector times the matrix. And if we do that, we get, and again, this is all less than or equal to 1. We end up with x1 minus xc1 squared, all divided by 4, plus x2 minus xc2 squared, all divided by 16, is less than or equal to 1. Now, hopefully at this point, you recognize that this is a ellipsoid from your calculus class. And we could certainly write this a little bit differently. So we could write this as 2 squared and 4 squared instead of 2 and 16. So if we know what our xc is, let's say I said, well, I want to center this ellipsoid at 5, 3. We would get something, an ellipsoid, that sort of looks like the following. So the minor, if we're going to divide this up into the minor and major radius, so here the minor radius is 2. And the major radius is 4. Okay, so where we started off was sort of some quadratic equation where we are multiplying it times p in the middle, right? And again, the eigenvalues sort of correspond, or the diagonal values, which are related to the eigenvalues, sort of had correspondence with the major and minor axes of the ellipsoid. Now, just like any ellipsoid, I'm terrible at ellipsoids, but you could also have a diagonal ellipsoid, right? It's certainly possible to have an ellipsoid that's sort of tilted on its side, and that works. And again, this would be a convex set, right? So I could pick any 2 points, and it would still remain within that ellipsoid if we started off with 2 points. All right, cool. Now, these ellipsoids and balls are just one type of norm. So they corresponded, if we went back up, this corresponded to the L2 norm, right? And the reason why we call it the L2 norm is right here, okay? So again, if you don't remember, if we want to generally write what a norm is, okay? So x to the p, or the p norm of x, well, that's equal to the pth root of x1 to the p power plus x2 to the p power all the way to xn to the p power, right? So in this case, 2 is just, we say p equals 2, and that's how we end up with square roots and squares. But there are certainly other types of norms that we can use. And two of the more important norms that we're going to use are the L1 norm and the L infinity norm. So sort of. So we can take other norms. All right. So to sort of reiterate this idea, we just saw that the L2 norm, or let's say that the feasible space constructed using the L2 norm, and the reason why it's usually we call it like this, L2, and that's how it gets its name, like L. Well, I guess if you're writing it in Spanish, it would be like L2, right? If you're writing it French style, maybe you'd write like that. I don't know, L2, right? So basically you're saying the letter L and then 2, right? So we just saw that if our feasible space is constructed using the L2 norm, and it's less than or equal to, it can be used to define a convex set. Now, I do want to maybe post a little bit of a caveat, right? So that caveat is, let's say we use the L2 norm and it defines some ellipsoid. All right, so maybe, I'm gonna. Okay, so this ellipsoid could be represented with some P. And what's going to happen is P is not just going to be a diagonal matrix with zeros and then 1 over lambda. It's going to look a little bit different. And that's actually what's going to create the tilt. But there's one requirement here, which is that we have a less than or equal to, right? If we don't have that, then we no longer have a convex set. So let's say we had something like x tilde p inverse x is equal to 1, right? Then the only points that are part of that set are the ones on the boundary of the ellipsoid. So not actually in the ellipsoid, but on the boundary. In that case, if we were to pick 2 points, right, and we tried to connect them, they wouldn't be on the boundary. So this is not convex. Okay. And alternatively, we saw that, and we sort of discussed this point, right, that if we require that the feasible set or the norm be greater than or equal to 1, then we're talking about all the stuff that's outside of the ellipsoid. Okay. So this is the same idea as the circle, right? So again, if we were to pick 2 points, right, and we were to try to connect them, part of that, just like the donut hole example earlier in the class, would tell us that we're not convex. Now, the neat part is, again, if we have this idea of x minus xc norm squared is less than or equal to r squared, well, that's convex, okay? So this L2 norm is convex. And then we can even do funny things with it, right? So we could say, like, what about if we multiplied it times x minus xc times some matrix A? Is that still convex? Well, yeah, it is. In fact, this A matrix could be a rotation matrix if you wanted to. And that could actually be used. That's another way you, oh, not that guy. That's another way you could construct a rotated ellipsoid. Okay. Yeah. Yeah. Okay. So there are definitely other types of norms besides these ellipsoids. right? So we have the L1 norm, right? That's a common norm that's used, right? And this one's, again, well, I'm gonna write it. So we write it with a 1 right there. And the L1 norm, it's sort of like a special version of this P norm, right? It ends up, if you do it, it ends up just being the sum of the absolute values. Okay. So you're taking the absolute value of each element in x minus xc, and then you're going to add them up, right? So again, this just comes from the definition of the P norm, right? So it's a sum of the absolute values. The other norm that gets used a lot in optimization is called the infinity norm, or the L infinity norm. Okay. So we write this, same way, x minus xc to infinity. And this one's a little bit weird. So it doesn't come directly from that P norm equation, but it's defined as the maximum of all your values in your vector. So you would take a look at the absolute value of x1 minus xc, right, and the absolute value of x2 minus x2c. And you'd keep doing this. You'd take the absolute values of all the components of x minus xc, right? And you'd figure out what the maximum value is, right, of all those quantities. And that's what the L infinity norm is given by. So it's sort of nice to have a representation of these in 2D space, right? So, oops. So if we have minimize some function f of x, and let's say we're going to subject it to, x minus, 5, 3, 1 norm, less than or equal to 5. Well, in 2D space, essentially what we're doing is we're moving over to the point 5, 3. 1, 2, 3, 4, 5. 1, 2, 3. So this is going to be the center of our L2 norm. And instead of, normally, let's say this was a L2 norm, we would draw a circle of radius 5. Okay, so that would normally be what we would draw. Oh, and actually, let me pick a smaller number so we can make this a little bit. Say 2. Okay. So normally, if I were to say, let's draw the L2 norm with radius 2, I'd draw something like, okay. So this what I just drew is the equivalent of x minus 5/3 2 norm less than or equal to 2. Okay, so it's a circle with radius 2. Now, in our case, we want to draw the 1 norm. And it's the same idea, but actually, in fact, instead of a circle, because we're taking the sum of the absolute values, it actually looks like a diamond. Right, so I'll draw this in green. Oops. And so this L2 norm is everything that's inside of this green diamond, which is kind of cool. So that's pretty useful. If you want to understand where that comes from, I think we could always look at the simple case where we just say the L1 norm is less than or equal to 1, right? So that would be the same thing using the L1 norm. That would be the same as saying x1 absolute value plus x2 absolute value is less than or equal to 1, right? So if we sort of draw what that looks like on a Cartesian coordinate plane, well, x1 is equal to 1 and x2 equal to 0 would certainly be in that point. Same with x2 is equal to 1, x1 is equal to 0. So we could go around, but we could only get a half of each, right? So if we were to do 1/2, x1 is equal to 1/2, and x2 is equal to 1/2, well, that would be less than or equal to 1, but we couldn't really go further than that, right? So that's kind of how we get this diamond shape. In hyperdimensions, right? So here we're drawing it in 2 dimensions. You could I'm not going to even really try, but certainly this still works in 3D space, right? I don't know how you draw it, but you'd have like some hyperdimensional diamond, right? So it'd be pretty neat. I'm bad at drawing diamonds, so maybe be something like that, right? You'd sort of have this diamond in 3D space. Now you'll notice something neat, right? So if we look at this feasible space here, we can actually write it using a set of linear equations, right? And that's really actually kind of interesting. So let's say we scaled this up. We'll keep it like that. So, if we look at this L1 norm in the feasible space that we have, we can see that it's defined by 4 different linear constraints, right, that are sort of used to build up a box. So here goes the 4 linear constraints, and I'm sort of pointing the arrows in the feasible direction, right? So in fact, the neat thing about the L1 norm is we can find a representation using a bunch of linear constraints. So in this case, the linear constraints would be, if we sort of go through and draw these lines, it'd be minus x1 plus x2 is less than or equal to 1. x1 plus x2 is less than or equal to 1. What else? X1 minus x2 is less than or equal to 1. And finally, minus x1 minus x2 is less than or equal to 1. And all these equations, right? So these 4 equations right here sort of correspond to the green lines that you see there. So one of the neat parts about the L1 norm is that we can actually write it as a set of linear equations. And again, this is going to be helpful as we start implementing some optimization programs, because we're going to be able to formulate if we ever have a problem with an L1 norm, we can formulate it and put it into CPlex. So that's super cool. Okay. All right, so let's now think about the L infinity norm. All right, so I'm gonna, which norm did other norms? Okay, so we talked about the L1 norm. The other norm that we commonly use in optimization is the L infinity norm. So let's say I had x minus xc is less than or equal to 5. Okay. This is equivalent. Again, this is like taking the max, right? So here we're saying what's the max of the absolute value of x1 minus xc1, and the absolute value of x2 minus xc2. And the neat part is that we can actually represent this using 2 different linear equations. Right? So, but they'll have to be expanded out a little bit. But for the most part, this L infinity norm is the same thing as saying, well, the maximum, so whether this guy or that guy is the maximum, it doesn't matter which quantity, the maximum of these two values has to be less than or equal to 5. So we could just sort of rewrite that as the absolute value of x1 minus xc1 is less than or equal to 5, and the absolute value of x2 minus xc2 is less than or equal to 5. Right? Now let's sort of visualize this in 2D space. So again, we sort of do the same idea where we go to the center, wherever the center is. So this is xc. Right? So we can pick whatever the center is, right? This is an arbitrary value. But this 5 here, again, still corresponds to the radius. So normally we would say, okay, here goes a circle of radius 2. Here goes my circle of radius 2. So this would correspond to the L2 norm if I was taking it, but I'm not taking the L2 norm. I'm actually doing the L infinity norm. And a good way, and I suggest you sort of go through it to understand it, but the L infinity norm looks like a box. Okay, so instead of a diamond, it's a box with radius 5. Okay, and so here we're going to have everything inside of that box. Okay. That's kind of cool. The radius will be 5, diameter will be 10. So okay. So what's like an application of these types of norms in an optimization problem? Okay, so maybe we should give an example of when you might use these L1 and L infinity norms. Okay. So let's say you're flying on an airplane or you're going to mail a package. Okay. So let's say you're shipping the package. Or actually, no, we're not going to do shit. We're going to say like you're taking luggage on a plane. You've probably seen some rules about luggage where they might say like, the sum of the length plus height plus length, height, width of luggage, right, is less than 20. Okay, so that certainly happens. They might also say, well, no one side of the luggage is longer than 12 inches. Well, this is exactly what corresponds to the L infinity and the L1 norm. So this guy here is going to correspond to the L infinity norm, right? Oh, no, not the L infinity. This is going to be the L1 norm, right? Because the L1 norm is taking the sum of the absolute values, right? While the L infinity norm is looking at the maximum of the values, okay? So if we had a piece of luggage and our goal was to maximize the volume, me might say something like, let's maximize x1 times x2 times x3, which is the volume of our luggage, where x1, x2, and x3 are the dimensions. So it's the width, height, and depth, or whatever, length, width, height. okay, of our luggage. But again, we might be subject to some constraints from the airlines where they say, well, you know, the sum of your dimensions has to be less than or equal to 20. So in that case, we would be saying that the L1 norm of X is less than or equal to 20. Okay, and again, the reason for that is that the L1 norm, that's equal to the sum of the absolute values. So that's the same thing of adding up the sides of our luggage. And then the other sort of constraint that we have is that no one side could be longer than 12. Well, we could just write that as the infinity norm of X is less than or equal to 12. Okay, so here goes a good example where we can use this L infinity norm and L1 norm in order to formulate an optimization based on some information that we were told. Okay. All right. One second. Okay, so if we have, again, so one of the big points here is this guy is convex and this guy is convex. It's worth discussing the relationship of constraints and how do we go about preserving convexity. So how do we know, I listed the L2 norm, the L infinity norm, the L1 norm, and linear equations are all convex. But can I do weird combinations of them or do weird things with them and still have a convex feasible set? And so it's worth discussing what operations that preserve convexity. Convexity, I hope that's spelled right. All right. So let's say we have, an optimization problem. With two sets of constraints, or two, basic sets of constraints. All right, the first one, or the first set of equations correspond to linear constraints. Right? So these are linear constraints. Right? Which we have shown these are convex, right? So if we have a bunch of linear constraints, they're convex. The other thing we've shown is that these quadratic equations where we have them less than or equal to a value, these are ball constraints and they're also convex. Okay. Now, when we put them together like this, what we're saying is all four equations must hold true. And essentially what we're doing is we're taking the intersection of these guys. So if I were to draw what that feasible set looks like, first I'm going to have, let's say something that looks like, oops, whoa, what's that? Something that looks like this. And, this triangle corresponds to the linear constraints. And then I'm also going to have a circle. So let's draw my circle. And, this circle, actually, let me draw these in different colors. Come on. There we go. All right. So again, for the triangle here, the linear constraints, we're going to draw this. The green area is the feasible area corresponding to that. And then for the ball, right, the feasible area is everything in the red. Now, when we put these together, the feasible space of all these constraints together is the yellow thing. Okay. Right. So this is the area that we're actually optimizing under. Okay. So our feasible set. So these four equations only define a feasible set that's given by this sort of like half circle. Okay. So that's all that we have for our feasible set. We're not taking the union of these things. We're not adding the red area to the green area to the feasible set. No, we're intersecting them, right? And when we do that intersection, we're only left with this half moon, okay? And so this is a function, the intersection of convex constraints are still convex, okay? So if I have a constraint equation, a set of constraints, and I add another constraint and another constraint and another constraint, and every constraint that I add is convex, then my feasible space will remain convex. Alrighty. Okay. So that's one of the first properties that we need to learn. So the adding of constraints, or what is effectively the intersection of multiple convex constraints, results in a convex set. And again, we can sort of see that with this half circle, right? It's convex, right? No matter what 2 points we select, we draw a line connecting them, still inside the set. The next important operation that preserves convexity are linear operators. Okay. And I'm not talking about linear constraints. I'm talking about passing our variables through a linear operator. So let's say I had f of x is less than or equal to c. If I were to say, well, let's, instead of doing this operation, what if I said f of a times x plus b is less than or equal to c? So here I'm taking a linear operation on x. This guy, so if f of x, whatever that function may be, is convex, then if we are to take a times x plus b inside of that function, that is also convex. Okay, so when might we do that? Well, we've already seen some examples of this, right? So let's give a quick example. So let's say I said the L2 norm of x is less than or equal to 2. Well, that's the same thing as drawing a circle of radius 2. Or a ball of radius 2. Okay, and it's everything inside. One thing that I could do that we have done is we moved it over, right? We shifted it. Oops, that's a bad circle. Okay. And so that, that might be the same thing as saying x minus, I think, 4, 2 norm is less than or equal to 2. Okay, so that would be this equation. So all we're doing is sort of shifting our x over. And again, it didn't change. You'll notice it didn't change the shape of the circle, just moved it. Now, if we were to multiply x times a, then we would definitely change the shape, but it would actually still preserve convexity. So that's a nice little thing to learn, that if we ever have a function, then we preserve convexity if we pass it through a linear operator. And in fact, that's what allows us to make ellipsoids. Okay, so before our function, we might have had our function as, x transpose x is less than 2, right? So that draws a circle. Right? If I were to say now we're going to multiply each x, so we're going to place x with y and we're going to multiply it times, or say y is equal to ax. Okay, in fact, let me even do it a little bit differently. I'm going to say, well, we'll just leave it like that. Then if I were to go through this operation, right, that would be like saying x times a transpose a times x is less than or equal to 2. This is pretty similar to what we had before with that P inverse, right? Okay, so in this case, a might be 1 over lambda, right? So if we do the 1 over lambda and we multiply it times itself, a transpose a, then we get 1 over lambda squared, which is this 1 over p. And we saw that transformed our circle into an ellipsoid. Okay, so that also preserves convexity. Another way that we can sort of that this A matrix comes into play has to do with down selecting. Okay, so another example. Let's say we said we want to minimize some f of x subject to some ball is less than or equal to 10. And I'm going to say x is actually a 3-dimensional vector. Okay. So if we were to plot this in 3D space, we'd be drawing basically a sphere. Okay. Of radius 10. Okay. But what if we didn't care about the third dimension? What if we only cared about x1 and x2 being within a circle, right? We could sort of down select, like we don't care about x3, the third dimension. Let's say we wanted to make a constraint that looked like a cylinder. Okay, so x1 and x2 has to be within a circle. but x3, again, we don't care about, as long as it's our x1 and x2 is within this cylinder. So we could do this with this sort of down selection process if we're a little bit smart and we pick the right A value. Right? So in this case, we'd say, let's take our x2 and multiply it times some matrix A. X would still be, not x2. X would still be part of the third dimension, but the trick is, if we wanted to do that, we would want to select A to be the following matrix. And in fact, if you go through and do the multiplication, you'll see what ends up happening as you drop out the third dimension. So let's sort of see how that happens. So let's say, we want to do AX and take the L2 norm. No, that's the same thing as saying 1, 0, 0, 0, 1, 0. We have this matrix. And we're going to multiply it times x1, x2 times x3, or x1, x2, x3. Okay. And then we're going to take the 2 norm. Okay. All right, so let's go through and do this multiplication, right? So if we go row times column, we end up getting x1, right? So for that first row times the column, we have 1 times x1 plus 0 times x2 plus 0 times x3. So we're only pulling out x1. Now, if we do the second row times the column, we only end up pulling out x2. Okay. And so you can see now we just care about taking the L2 norm of x1 and x2, but x3 can be anything. We're not constraining it. So in that way, we're saying that x1 and x2 have to live within a circle of radius 10. But x3 can be anything. So this is the equivalent of having a constraint that is a cylinder. Okay. So that's kind of cool. So again, I'm going to sort of repeat another idea that we sort of harped on of how we can use these linear operators. Right? So this is a linear operator on X, and it will preserve convexity. Right? So we can do down selecting of specific dimensions. And we sort of discussed this, but we can do stretching and rotation. Right? So we saw ourselves make ellipsoids, but you can do the same thing with the L1 norm. Right? So let's say I have some constraint where I want x1 norm to be less than or equal to 1. Right? So the 1 norm, again, it's sort of like this diamond shape. Now, let's say we let, I'm going to just pick some matrix A, 0, 2, 0, 5. Oops. And I'm going to say, well, I want A times X, 1 norm, to be less than or equal to 1. What does that look like? Okay. So let's go through and do this multiplication, right? So we're going to take 2, 0, 0, 5, and we're going to multiply times x1, x2. Then we're going to take the 1 norm. Okay, so if we go through and do this multiplication, row times column, we end up with 2x1 and 5x2. So that's the vector inside of the norm. That L1 norm has to be less than or equal to 1. If you want to, the way we could, there's a few ways to expand this out. One way would be the absolute value of 2x1 plus the absolute value of 5x2 is less than or equal to 1. Okay. Let's see how this affects it, right? And usually, because it's a diamond and we know the shape of the L1 norm, all we have to deal with is the endpoints, the caps, right? So we can pretend what happens if x, we're going to start by saying if x2 is 0, what's the biggest x1 could be? So what are the x and y intercepts? So in this case, when x2 is 0, x1 can only be 1/2. And actually, let me draw it differently. This tiny. I'm going to go. So let's say this is 1/2. Okay, so if x2 is 0, 1, 2, 3, 4, then the sort of points of the diamond can be 1/2. Okay, because 2 times 1/2 absolute value is equal to 1. In the other dimension, the biggest that x2 can be if x1 is 0 is 1/5. Okay, so where is 1/5? I think 1/5 is about somewhere about here. I don't really know, but you're going to end up getting a stretched out diamond as your feasible space. Okay. And so there's all sorts of ways that you can do this, and it's pretty nice because again, remember, like if you remember this P inverse where we talked about the 1 over lambdas, right? And how these sort of affected the dimensions, right? It's the same idea. You just have to be careful. So here we're not taking the square because it doesn't make sense, and so we're working in the rate, like the dimensions of the radius. So you can see that when we multiply times 2, we're shrinking the radius by 1/2. If we multiply times 5, we're shrinking the radius by 1/5, right? So that's kind of what's happening here. So with this sort of trick, let's say we just pick some arbitrary a, and I said it was 1/10, 0, 0, and 1/4. Well, and we are to say what's the feasible space for the L1 norm less than 1. Well, it'd be pretty straightforward. It would give us, again, probably some sort of diamond, right? Oops. We get some diamond like that, where this would be x1 equals 10, x2 equals 0. Here we would have x1 equals -10, x2 equals 0. Here you'd be x1 is equal to 0, x2 is equal to 4, and x1 is equal to 0, and x2 is equal to -4. And so everything inside of here, inside of this stretched out diamond, where the axes, right, or the radiuses along each axis are given by the values in this A matrix. Okay. So there's a pretty good primer on convex sets. Let's go ahead and take a break, and we'll join back up to talk about convex functions at 3:25 p.m. Okay. All right, cool. So I'll see you guys in about 10 minutes. Okay, alrighty. So one thing that I want to do is I want to encourage everyone to actually go through and work out the math of why this works out. Okay, so like, sure, you might believe me and just take it for granted that the one norm is a diamond, and if I multiply times some matrix, I stretch it out. But really, if you take the approach of just like, oh, L1 norm, diamond, L infinity norm, box, L3 norm, circle. You're not really doing yourself justice in learning this material. So I would definitely encourage you to sort of work through how do I get this particular box, right? If I know that the L1 norm is equal to this equation. So what I want you guys to do, you guys haven't really learned unless you can draw that feasible set on your own, right? So please make sure to do that. All righty. All right, so we've talked about, at this point, convex sets. The next thing that we're going to talk about are convex functions, okay? And again, the whole idea is, in order to have a convex optimization problem, we need to satisfy two conditions. One, we need to ensure that our set that we're working with is convex, and that the function that we're working with is also convex. So we've already gone through and sort of figured out, okay, what are some examples of convex sets? What do they look like? What are some operations on those sets that preserve convexity? We're now going to go through a similar process with functions. The basic idea is, well, if we have some minimize or maximize function subject to x being in some set, right, we're now going to look at this function here, right? And when does it have specific properties that allows us to optimize over it? Now, in our case, if we have a minimized problem, we want to make sure that our function that we're evaluating is convex, right? So a convex function, if we draw it, it looks like a bowl shape, okay? Now, if we're doing a maximized problem, we actually want a concave function. Right? Concave function is just an upside down bowl, more or less, right? So looks like that. So it just flipped in the other direction. And that sort of makes sense, right? Because you want to find the maximum, the highest point, right? And if you were to try to find the highest point on this green line, it wouldn't really make sense, right? But for a minimum, you want to find the lowest point, right? Which actually, does make sense. There is just one lowest point with a convex function. So again, if you're minimizing, you want a convex function. If you're maximizing, you want a concave function. These are pretty similar. We're going to talk about everything in terms of convex for now, but we can easily find the equivalent representation for concave, but I'll sort of try to pull that together at some point. All right, so what is a convex function? So a function is convex over a domain and by domain, we just mean the feasible space, or whatever our constraint set corresponds to. If for any 2 points in that constraint set, and some value theta between 0 and 1. Oops, and I should write a function f of x is convex. If the following holds, that alpha x1 plus 1 minus alpha x2 is less than alpha f of x1 plus 1 minus alpha f of x2. All right, so what does this even mean? Well, I'm going to draw a graph. Let's pretend this is our function f of x. Right? So this black line. And maybe our domain that we're going to allow is everything in between these two values. Okay, so this is going to correspond to our feasible set. Any x that's between, let's say, -1 and 1, 2, 3, 4, 5. Okay, so that's our feasible set. And so we're going to pick 2 points. Um, 2x, so here goes x1, and here goes x2. So this point here is f of x2, and this point here is f of x1. Now, if we select some theta, right, so this might be the convex combination, so we'll call it x prime. So x prime is equal to theta x1 plus 1 minus theta x2. All right, so that's just what is inside of the function. Okay, so that would mean this point right here corresponds to f of x prime. All right. So what we're saying is that value, okay, this yellow guy, which corresponds to the evaluation of that function, is less than the convex combination, and I'll draw these guys of red, of f of x1 and f of x2. Well, what's the convex combination of f of x1 and f of x2? Well, it's the line that goes through these green points, okay? And so the basic idea is, well, any line connecting 2 points on your function has to be greater than the evaluation of that function at the point between those 2 points, right? So again, in other words, this yellow point has to be under the red line, okay? And it doesn't matter what 2 points you select, right? So let's say I picked, I'll select another 2 points. So let's say I picked this point and that point, okay? And I draw a line connecting them on the function. Oops, that's not right. Okay. The average between those 2 points on the line is still underneath that red line. Okay. And so this is sort of a mathematical definition of how we define a convex function. Now, there's going to be some tricks that make life a little bit easier. But let's sort of see some examples of convex functions. Okay. Oops. All right. So one example that we've already dealt with is just a linear equation. Okay. So here f of x is equal to ax plus b. And as long as a and b are real numbers, then we're okay. This is a convex function, okay? And we can actually prove this if we wanted to. Again, we would just need to check that this inequality holds true. Okay, but you could certainly do it and work it out, and it will absolutely hold true. Another example of a convex function is an exponential. So f of x is equal to e to the ax, right, where a is a real number. That's also a convex function. Let's see what else we got. If we're a little bit careful, all powers are also convex, right? So like quadratics to the third power, fourth power, fifth power. So f of x equals x to alpha. But this is only true, we do have to be careful. This is only true for alpha greater than or equal to 1, or alpha less than or equal to 0. And it's also true, you got to make sure that x is greater than 0. And the reason for that is, let's say the example, we want to be careful is if we did x to the third power, we'd get a function like that. And so you could imagine I could pick 2 points. So I'm going to pick 2 points right there, and we'll draw my red line. Okay, and I said that the point between them has to be less than the red line. Clearly that's not happening here, right? And there's sort of this kind of rule that we can follow, right? So I sort of said it at the beginning, convex functions are bowl-shaped, right? Now the linear is sort of a special case, and we'll see why, but this exponential is kind of like a bowl, right? And this power is kind of like a bowl. If we just look at, 1/2 of it on this side, it looks like half a bowl. But for the x to the third, if we consider, we allow x, the domain, to be negative, it's not a bowl, right? This shape is not bowl shaped. It's got to be able to hold water, kind of, right? Now, to sort of make up with that, we could say, well, what about the absolute, if we take x and we take the absolute value and then we raise it to the p power, well, yeah, that would be convex, right? Because then we'd have something like that. But again, we just require that p is greater than or equal to 1. So again, this is convex. For, I do suggest that you go through and plot what p less than is equal to 1. That looks like that, right? So the bowl is pointing down instead of pointing up. So this is, p is less than 1, I think between 0 and 1. So this is not convex. And again, we can sort of demonstrate that if we pick 2 points, we draw a line between them. And the corresponding point that's supposed to be any point on that function is supposed to be below the red line, right? But I picked 2 points where there is obviously the function is above the red line. So we're not convex in that point. In fact, what we are is we're concave. Okay, so for a maximization function, that's okay. But for a minimization, that's not okay. Another example of a convex function is the absolute value. Okay. That's a convex function. Again, we can pick any 2 points and connect them with a line. And you'll see our function is always below that red line. So that's good. All right, so we're convex. Let's do a couple proofs. And the proof is going to use the inequality here. And this is a special inequality. It's called Jensen's inequality. Okay, so we're gonna do a couple of problems to prove convexity, just so you can sort of see the structure of it. Actually, so what else did I want to say? Yeah, okay. All right, so let's do an example problem to prove that something is convex. Let's show that f of x squared is convex. All right, and we're going to do this using Jensen's inequality. All right, so we want to show that f of theta x1 plus 1 minus theta x2. And the question is that less than theta f of x1 plus 1 minus theta f of x2? All right. So let's start filling in and applying our function x squared, right? So, we can sort of, I'm just going to copy this because I think it's a little bit faster maybe. All right, so we're asking this question. We're going to square all these functions. Oops, function. So we're going to have x1 squared, and then we're going to have x2 squared. And then again, on the left-hand side, the whole quantity squared. So we can go through and multiply all this stuff out. We get theta squared, x1 squared, plus 2 theta, 1 minus theta, x1, x2, plus 1 minus theta squared, theta 2, not theta 2, x2 squared is less than or equal. And again, this is sort of the question that we're asking. Theta x1 squared plus 1 minus theta x2 squared. All right. Now we can see some opportunities to cancel stuff out. So on the left-hand side, we see this theta x1 squared, and we have it on the right-hand side, so we can subtract both off. And then what are we left with? Oh no, actually I can't even do that cancellation, right? Because there's a squared here, and we don't have a square on the other side. All right, but let's go ahead and maybe, I guess I see in my notes, I put everything over to one side. All right, so we're gonna check, I'm gonna move all this stuff over to the other side. So we're gonna check if 0 is less than or equal to all this other stuff. All right. So I'm gonna try to organize it a little bit. So I'm gonna organize it by the variable. So I have x1 squared minus theta squared x1 squared. Next, we'll have 2 theta, 1 minus theta, x1, x2, plus 1 minus theta, x2 squared, minus 1 minus theta squared, x2 squared. Okay, at this point, we can start to sort of factor stuff out nicely. Right? So we have an x1 squared, and we have theta minus theta squared, minus 2. So this we're not really going to touch quite yet, but we will a little bit in 1 second. And if we look over here, what do we get? So we can pull out this x2 squared, and we're going to get 1 minus theta minus 1 minus theta squared. Okay. All right. Now the trick here is we actually see a repeating term all over the place. So I'm going to pull out this theta, and we get 1 minus theta. Okay, so this term is going to show up almost everywhere, and we're going to be able to cancel it out. All right, so here goes that 1 minus theta term again. And of course, we see 1 minus theta throughout this whole thing. So we can factor it out. And when we factor it out, we get on the inside 1 minus theta. Okay. So again, because theta, we've restricted it according to Jensen's inequality to vary between 0 and 1. We can divide by 1 minus theta without too much worry, okay? So we'll just sort of ignore the case where it's 1 minus 1 and we're dividing by 0, because in that case, all this stuff is equal to 0. So just to be clear, so when 1 minus theta is equal to 0, then we end up with 0 is less than or equal to 0, which holds true. So that's okay. So now we're going to consider the case where 1 minus theta is greater than 0. And so with that, we can sort of divide out 1 minus theta, and it's not going to change our inequality. Okay, so we can divide both sides by 1 minus theta. And we can simplify this quantity here to just get theta. So that's kind of nice. All righty. So now we see theta all over the place, right? So they all have this common term. So we can go ahead and divide by theta. And again, theta is going to be between 0 and 1. And we sort of dealt with the, we can sort of deal with the situation of when it's 0, it sort of devolves to the nominal case of, again, if you look here, if you plug in 0, everything sort of cancels out and you end up with 0 equals 0. So really, we just care about the case when theta is between 0 and 1 exclusively. So dividing by theta is non-problematic. And we end up with x1 squared minus 2 x1 x2 plus x2 squared. Now this we can easily factor, right? So again, we still have this question mark. Is this in fact true? And if we factor our equation, we get x1 minus x2 quantity squared. Now, this quantity, if you take the square of any number, it's always positive. Right? So what that means is, in fact, this inequality holds true. Okay? So that tells us that we've satisfied Jensen's inequality. And in fact, so this implies that f of x equal to x squared is convex. Right, so that's cool. All right, so there we go. So this is one of the ways that we can prove convexity. I'll do another problem. So this will give you some nice little practice. So let's do another example of a proof using Jensen's inequality to prove convexity. So let's say we have f of x is equal to the absolute value of x. So again, it looks sort of like that. We're going to apply Jensen's again. So let's go ahead and state Jensen's. So this is the inequality that we want to verify. All right, so let's start plugging in values. So we're going to get theta x1 plus 1 minus theta x2, absolute value. Less than or equal, and again, that's the question that we're asking. So that's going to be theta x1 plus 1 minus theta absolute value x2. Now at this stage, we're going to apply a trick that corresponds to the triangle inequality. So you probably learned this in your calculus class at one point, I think. So the triangle inequality says that A plus B is less than or equal to, or the absolute value of A plus B is less than or equal to the absolute value of A plus the absolute value of B. Essentially what we're saying, the reason why it has the name triangle inequality is we're saying that the sum of two sides, A and B, is greater than the length of C. So that's essentially, how it got its name, triangle inequality. So we can apply that here. And so when we apply that, we end up with the following. So this is what we started with. We're going to apply the triangle inequality. So that means it's going to be less than or equal to theta x1 plus 1 minus theta x2, right? Which is less than theta x1 plus 1 minus theta x2. Okay. So we still, we're asking this question right here. So we haven't really changed too much, but if we can show this quantity is less than that quantity, then that implies it's the first quantity is less than the third, right? So it's sort of, if one follows the other, then we're okay. Now, because theta and 1 minus theta are going to be between 0 and 1, they're always going to be positive numbers. So we can pull them outside of the inequality. So when we do that, we get theta times the absolute value of x1. And again, we can pull out 1 minus theta here from the absolute value. And that's because we know theta and 1 minus theta are positive values, or at least non-negative. And in fact, that is equal to what's on the left-hand side, right? So, but I'll keep it as the less than or equal to. But that certainly satisfies the inequality, right? So we got a check mark here. So in fact, what we were able to show is that theta x1 plus 1 minus theta x2 is less than or equal to, oops, and I need absolute values here. The absolute value of x1 times theta plus 1 minus theta times the absolute value of x2. So again, there goes our proof of that the absolute value of x is convex, and we did that using the triangle inequality. So just a little trick. So there are some really neat properties associated with convex functions. Right? And these might be a little bit easier to use than Jensen's inequality. The first one, let me write this down, additional properties. Of convex functions. So the first property of convex functions that we're going to discuss is the first order condition. Right. And the first order condition basically says all convex functions, if we pick a point on that function and we draw a tangent line on that point, then that tangent line is below the function. And so you can think of it as like sort of holding up the function, right? And this has to be true for all tangent lines to the function, right? So the way we would state that is that f of x0, where x0 is the tangent point, plus the derivative of f of x at that tangent point times x minus x0 is less than or equal to f of x for all x in whatever the constraint set is. And again, x0 is somewhere in the constraint set. Later on, we're actually going to use this property to approximate functions. So let's say you have some function here. One little neat thing is, if you draw a lot of tangent lines, they kind of hold up the function, okay? And you can actually approximate very complex functions using a bunch of tangent lines. So that's pretty neat idea. We'll do that in the next lecture. All righty. The next condition that convex functions satisfy, or a property of them, is the second order condition. And this is probably the one you guys know most, right? From your calculus class when you're undergrads, when you guys talked about convex functions or concave functions. The second order condition just says, a function is convex. So a function f of x is convex over its domain if the second derivative evaluated at all x is greater than 0 for x in that domain. Okay, so this is basically the second derivative test, right? So let's sort of give a quick example of that. So let's say we had the function f of x equal to 5x squared plus minus 10x plus 6. All right, so we can take the first derivative. What do we got? 10x minus 10. And then we can take the second derivative, and we get 10. And that's certainly greater than 0, right? So that sort of fits this idea that it's bowl-shaped, right? And it's, second derivative is positive, and, this is concave. And again, you can sort of see the idea that if we draw any tangent line to the function, it's sort of below the function itself. So this is a neat little property. And again, you can apply it all over the place. So this is a nice little check, right? So instead of using Jensen's inequality, sometimes you can just use the second derivative test, right? So like for an exponential, all right, you could take the first derivative, you get a e to the ax, and then you could take the second derivative. All right, these exponentials are always greater than 0. And that a squared is always greater than 0. So that implies that the second derivative is always greater than 0. So our function e to the ax is convex. Okay. Another neat way to check for convexity is to use something called an epigraph. An epigraph is basically, well, let me give you the rule, and then I'll draw an epigraph for a function, and you'll sort of get it. You'll go, oh, okay, I get it. So if f is a convex function, so f is convex if and only if the epigraph of f is a convex set. Okay, so what's an epigraph? Well, an epigraph, basically what you're doing is you're taking your function and you're going to fill in the area above the function. Okay. And this area above the function, you're going to check, hey, is this red stuff convex? In this case, it is. You can take like a convex set. You can take any 2 points, connect them, and they're still in the set. So what you do is you're effectively taking your function and then saying, hey, everything above that, let's pretend it's a set. You're augmenting, you're defining a set based on your function. Okay, so it's kind of neat. Yeah. Okay. So we can see cases where like this makes it pretty easy to see why a function would not be convex. So let's think about a sine function or something like that. Certainly if we drew the feasible set, or we drew the epigraph corresponding to that sine function, and then I were to pick 2 points, right, in that set, it would certainly not be a convex set because for part of it, you'd be outside of your epigraph for that set. So here we're not convex. All right, so the sine function is not convex, and in fact, it's not even concave, right? So, you're not going to ever get anything out of that. So these are hard to optimize. And again, we sort of can understand why, because at the beginning of the lecture, I said, well, if you have multiple local optimums, right, whether they're peaks or valleys, or if you're minimizing or maximizing, that's problematic, right? So this is a good example of one of those. Now, there are some properties, some useful properties of convex functions that will tell us like, hey, if we compose or make new convex functions or try to, manipulate a convex function, is it still a convex function? Okay. So let's sort of go over a couple of key examples. So the first example is scaling. Oops. Okay, and again, this is the same idea of linear transform on a convex set is still a convex set. So essentially, if you take alpha and you multiply it times your function, that's convex. Oops. If f of x is convex, and alpha is greater than or equal to 0. If it's less than or equal to 0 and you're multiplying times -1, you're sort of flipping the function upside down. So then it's going to become concave. Okay. The other way we can preserve convexity by manipulating our functions is through composition with linear functions. And again, this is the same idea as sets. So what do I mean by that? F of AX plus B is convex if f of x is convex. All right, so what's a practical application of this? Well, I told you that the absolute value of x is convex. So that means if you were to try to minimize a function that was like 5x plus 3, well, that's also a convex function. So that's nice. So we can make a more complicated function using sort of some basic convex functions, and we'll still know that they're convex. The last property that we're going to discuss, that again, this is actually going to help us in approximating nonlinear convex functions, is something called the pointwise maximum. So let's say we have some f of x, and it's actually the maximum of a bunch of different functions, right? So we have f of x1, f of x, or f2 of x, right? All the way to fm of x. So we have a whole bunch of functions and we're taking the maximum of them. This function, which is the maximum of functions, is convex if f1 all the way to fm are convex. All right, so let's do an example of that. Let's say I have a parabola and a line. Okay, so this line f1 of x is equal to x plus 3. And I told you at the beginning of the lecture, this is a convex function, right? It's linear. The other one, f2 of x, is equal to x squared minus 2x plus 2. And through the second derivative test, we know this function is convex. All right. So if we are taking the maximum of these two functions at any point, the maximum, so if I were to write f of x is equal to the max of x plus 3 and x squared minus 2x plus 2, okay? Then that corresponds to the yellow line that I'm drawing here. Okay. And that yellow line is convex, right? That function f of x, where we're taking the maximum between multiple functions, is convex functions, is convex in itself. Right? So again, we're going to use this in order to approximate. So this is the property that lets us approximate. Let's say here we have this convex function. Right? Cplex might not let us represent it because we can't type in the equation. And we'll go into why a little bit later. But one thing that we can do is we can say, well, let's take a whole bunch of tangent points and draw tangent lines. Right? Oops, that was a bad one. Right? If we take the maximum of all these tangent lines, that will define the following function, right, that I'm drawing in yellow. Now, it's not a perfect approximation, but it's pretty dang good. Okay. So this is one way that by taking a maximum of a bunch of tangent lines, we can actually approximate a nonlinear function just using linear equations. Okay, so with that, am I gonna end lecture? Yeah, I'm gonna end lecture. And next week, we're gonna talk about how do we program these L1 and L infinity norms and nonlinear functions into Cplex, okay? So with that, I'm gonna wrap up. Just FYI, I have designated family time this weekend, so I will not be answering any emails over the weekend. So if you have questions about the exam, I will not be answering them. So that's my heads up for you, or at least don't expect a quick response. All right, that's it. Unless there are any questions or concerns. No. Okay, all right, I'm ending lecture. Have a good one, guys.
Thank you, Professor.
Yep, thank you.
Have a good one too.
Thank you. Have a good one.
Okay.